Hi everyone, we are Team Robo Erectors and we are participating in the RoboCup Singapore Open 2024. Our team is composed of our team leader Darwin and the main programmer Zheng. We are both from Singapore and are final year students at Singapore Polytechnic. We assisted in the organization of RoboCup Singapore Open 2023, and this is the second time we have come together to work as a team to compete in this prestigious tournament.
The CoSpace rescue is to collect as many colored objects as possible in 6 minutes, and the competition takes place on a map that includes traps, deposit zones, swamps, obstacles, info lost zone, and special zones. The main objective of CoSpace rescue is to collect as many colored objects as possible in 6 minutes. The special zones will double the points acquired. Entering an information loss zone will result in the robot losing its coordinates. If the robot ventures into a trap, it will forfeit all the points and objects it has gathered. The swamp area will reduce the car's speed by 80%. The virtual car used in the RCAP CoSpace Rescue Challenge University Advanced category is equipped with a variety of sensors to aid in navigation and object detection. The car has 2 sets of color sensors to detect RGB colors on the map, 3 sets of ultrasonic sensors to detect obstacles, a gyro sensor to sense the orientation of the car, and the X, Y coordinate of the car is provided by the game. We will be moving on to explain the strategies we have used for this competition. Firstly, we will be discussing the object collection and depositing strategies. As the object's size decreases, its score increases. The point values for the objects are as follows: red, 10 points, cayenne, 15 points, and black, 20 points. This makes it more challenging to pick objects with higher point values. Each robot can carry a maximum of 6 objects. If the robot collects a set of objects in the sequence RGGD and deposits them, it will create a Super Plus object on the spot, which is valued at 180 points. This unique object can only be collected by the team that created it. Additionally, if the robot collects a set of objects in the sequence RGB and deposits them, it will generate a super object with a value of 90 points, similar to the Super Plus object. We attempted many potential combinations to see which combination of objects would allow us to collect the most objects while collecting up to 6 objects, which explains why there are only 6 letters in the combination value table. Generating one super object while going to collect the normal object which gives the most points, which is black, only gives out 20 points, is only 390 points. However, if we attempt to collect the Super Plus object, it will give 540 points, which is 38% more than generating a super object. We have defined the robot to have 2 phases throughout the game, Phase 1 and 2. During Phase 1, the robot will collect 4 sets of RRGGB to obtain the generated bonus points of the Super Plus object. This renders the combo to be the most optimum in maximizing the number of points we can get. During Phase 2, the robot will attempt to complete as many sets of RRGGB combinations as illustrated in the photo. We will next move on to bit mapping as mentioned earlier. Bit mapping is a digital image format that represents graphics and images as a grid of individual pixels. Bit mapping will also be used with a star implementation in mind, aside from preventing the robot from driving out of the map. We assign 3 colors of the value of 0, 1, and 2, respectively. These 3 distinct values will create the map for the robot to understand. Each value will have different costs, where areas without obstacles have a cost of 0, meaning that the car can freely roam. The cost for swamp areas and obstacles is much higher, so that the robot will avoid taking such paths. So, how can we apply bit mapping into CoSpace Rescue? We continued coloring the map according to how we want the robot to act with the map under different circumstances. The free areas are assigned to a value of 0. The swamp is assigned to a value of 1, while 2 represents the walls and obstacles. There will be 2 different maps generated, one with traps on the left and one without traps on the right. The purpose of converting the map into one without the traps is when the robot is not holding any objects. This allows the car to go through the other traps and save more time. Next will be zoning. We noticed that each map would have different object spawn zones. Here is the short clip of the map with varying object spawn locations on the left side. Therefore, to come up with the most optimal zones, we have decided to stack and overlap all these images to find the common pattern where which areas would have spawned a certain object. After finding which areas of the map have a higher probability of spawning objects, we will break down the map into the following zones with the indicated colors and the zone sizes. There are instances where the zones can have more than one color as indicated in the image. The robot will search these zones if they need to find a specific color. For example, the robot needs to get the last red object to complete the RRGGB combo. It will drive to the zone with the red objects defined in the bitmap. This will help the robot to be able to obtain the right objects it needs more rapidly, and therefore, it will churn out the Super Plus objects at an even faster rate. We will then convert the rectangular zones into a bitmap array, where the robot will be able to transverse inside to collect the specified objects. We will take the lower left corner of the rectangle box coordinate values, zone, yon, and upper right corner values of the box, stu, I2. These values will essentially form a rectangle, and upon entering these values into our executable object zoning generator, we will get an array as seen in the text file. When choosing which zones to get higher priority, we will factor in two primary reasons: whether the zones would give double points and where there is a higher concentration of objects. These zones can then be arranged in an ascending order in terms of importance. Zones that give more points or consistently generate more objects are of higher precedence than normal zones. We also explored the possible paths or pathfinding to identify the optimum path that takes the shortest distance and time to travel. We narrowed down 3 possible pathfinding algorithms that we can explore, all of which are used to find the shortest path to the end goal. To pick which is the best and most appropriate algorithm to utilize for finding the shortest path, we must first understand how each algorithm works before using it, and we have chosen 3 algorithms to work on at first. Dijkstra's algorithm is a popular algorithm for finding the shortest path between nodes in a weighted graph. The algorithm maintains a set of visited nodes and their tentative distances from the start node. The algorithm repeatedly selects the node with the smallest tentative distance, updates the distances of its neighbors, and marks it as visited. This process is repeated until the algorithm has visited all nodes, or the target node is reached. Greedy search is a general algorithmic paradigm that makes locally optimal choices at each step with the hope of finding a global optimum. In the context of finding the shortest path, a greedy algorithm selects the neighbor with the lowest cost at each step, without considering the overall path cost. The A* algorithm is a heuristic-based search algorithm. It's an extension of Dijkstra's algorithm that uses a heuristic function to guide the search towards the goal node. The heuristic provides an estimate of the remaining cost from a node to the goal, which allows A* to make more informed decisions about which nodes to explore next. A star maintains a priority queue of nodes to be visited, where the priority is determined by the sum of the actual costs to reach a node from the start plus the heuristic estimate to reach the goal from that node. Upon consideration, a star is best as it considers both the actual distance from the starting point and the estimated distance to the goal. This dual-factor approach enhances the efficiency of the search process. In contrast, Dijkstra's algorithm leads to potential time wastage by exploring irrelevant nodes. On the other hand, greedy best-first search may overlook the shortest path. So, how did we implement A* into the challenge? First, let's dive into the overview of a star, which includes initialization, open list, cost function, F-score exploration, and termination. Imagine the robot has 2 possible paths towards the deposit zone. First, we define the start, which is the robot's current location, and the goal, which is the deposit zone. Then we note down all the possible paths that we can take and store them in an open list. In order to calculate which is the best path, we have to use a few functions like g of n, the cost, to reach node n from the starting node, and h of n, which is an estimate of the cost to reach the goal from node n. Afterwards, we calculate the f-score by summing up both values. In the exploration stage, we start with the node with the lowest f of from the open list. The lower f-score means lesser distance we have to travel. The node is then expanded and its neighbors are added to the open list if they have not been evaluated before, or if a lower cost path to them has been found. Then we terminate the search after finding the shortest path after factoring both cost and distance functions, and the goal node is selected for expansion. The robot will now have the shortest path to the goal. Now onto the overview of our code. This flowchart demonstrates the logic that the robot goes throughout the challenge. First, we check if there is still time to collect objects. If the robot does not have enough objects to deposit, the objects the robot will attempt to find depends on the current phase. The robot will return to its object collection phase until 6 objects or X number of super objects have been collected, after which the deposit function is initiated, and the robot will drive to the deposit zone using a star. Here's a quick demo. Try to observe our robot collect RRGDB combos and then collection super object. We use several AI tools to help us in this challenge. Firstly, we have a custom large language model that was made in-house specifically for RoboCup CoSpace Rescue. It serves as the foundation for a chatbot that is able to assist us with information that is largely relevant to the challenge. We take it one step further with ChatGPT, which is a widely used tool today. It has been useful in giving suggestions on how to improve our code. Next, we used artificial intelligence text-to-speech to generate the voiceover for this very video, as well as Adobe After Effects for editing and creating our mascot. Now on to applying the knowledge gained to the real world. Technical implementation for earthquake search and rescue operations. In our approach to earthquake search and rescue operations, we have developed a highly advanced system that seamlessly integrates cutting-edge technology and robust algorithms to optimize survivor detection and extraction. We begin by deploying a drone equipped with thermal imaging and LiDAR systems. The thermal imaging capability allows us to identify survivors emitting higher temperatures, while LiDAR technology creates detailed 3D maps of the disaster area. This data is then processed to generate a comprehensive image, isolating critical information such as survivor locations, obstacles, and potential rescue points. Processed data along with GPS coordinates and LiDAR is transformed into a bitmap representation. This grid-based structure provides a detailed overview of the disaster site, with distinct values marking obstacles and survivor locations. It serves as the foundational data structure for our pathfinding algorithm. Using the A-star algorithm, our rescue robot calculates the shortest and safest path to reach survivors based on the bitmap data. It factors in the information from LiDAR to navigate around obstacles and choose the most viable route. Real-time feedback and coordination are critical components of our system. The optimal paths, survivor locations, and obstacle data are relayed in real time to officials and helpers on the ground. This information guides response teams to efficiently and safely reach survivors, ultimately minimizing response time. By employing this integrated system, response teams can significantly reduce the time spent on locating survivors, allowing for more effective rescue operations. Additionally, the use of a star path planning with bitmap data ensures that the chosen paths are both safe and efficient, prioritizing the well-being of both survivors and rescue teams. In conclusion, we learned the importance of strategic planning and how good planning can improve the outcome, like employing effective bitmapping or how to come up with a highest points object combination. Secondly, we learned about the various pathfinding algorithms such as a star, greedy first search, and 𝙍𝙤𝙗𝙗, which gave us a clearer insight and understanding on how algorithms work and how to code them out. Lastly, we learned about how to work in a team despite not knowing each other prior to this competition and coming from different backgrounds. The robot generally can generate 2,600 points on average, and the performance of the car depends on the map and the strategies employed by the opponent as well. However, overall it is good at obstacle and swamp avoidance thanks to the effective bitmapping. We would like to take this opportunity to thank our seniors and mentors, as their crystal clear instructions and guidance were instrumental in developing the team. We want to acknowledge RCAP's efforts in planning RoboCup Asia Pacific 2023. Moving on, we would like to employ our code to save more lives in natural disasters, like earthquakes or tsunamis, as we build our code to be flexible and applicable in such scenarios. We hope that our passion in coding can save more precious lives during such unfortunate situations. We also will be giving back to the community by using CoSpace Rescue as a platform to teach underprivileged kids coding. Thank you.